Good day and welcome back for the third part of our discussion on enclosed areas. So in our previous videos, we've kind of built up this idea that to find an area enclosed under a curve, for example, let's maybe think underneath the graph of the function f of x equals x squared on the interval from 0 to 1. So this kind of red shaded area. In order to calculate that area, the observation we made previously is I don't have any one single geometry type formula I can apply, but instead what we could do is first think about approximating it using rectangles underneath this curve and adding up those areas of the rectangles to approximate the area. And we finished our previous discussion by asking, well, how do we then get a better approximation? And of course you immediately told me we use more rectangles. So naturally we might ask, how do you get the best approximation? That is, what is the exact enclosed area? And theoretically you might say, well, we need to use infinitely many rectangles, which in practice we certainly can't do, but this idea of using something infinitely large brings us back to the idea of a limit. So we said, well, if we could somehow calculate what we had called the right sum using n approximating rectangles, we could take the limit as n goes to infinity to get the exact enclosed area. And before jumping into discussing how this is going to work in general, I always find it best whenever possible to look at a nice concrete example. So we're going to go back to this familiar example from our previous video. That is the function x squared from 0 to 1, and we are going to determine the exact area enclosed underneath the curve. So kind of the idea behind how we would do this. So we have said above that the area is going to be the limit as n approaches infinity of r sub n. So there's two parts here. The first part is we need to find or determine a formula for r sub n. So find a formula for r sub n. And note the formula for r sub n is going to involve n. And once we find that formula involving n, then we take the limit. So I'm going to go ahead and zoom in a bit on our picture. So in order to find r sub n, I want to think about this very geometrically. We are going to use n approximating rectangles. So we will use n rectangles, and we want them for convenience to all have the same base length. So we'll say with base length given by this quantity we previously referred to as delta x. So it's the length of the entire interval, 1 minus 0, divided by the number of intervals or subintervals we want to break it up into. So in our case, this would be 1 over n. And if I draw kind of a little mini number line underneath our x-axis, we have 0, and we're going all the way to 1. And when we break this up into n equally spaced subintervals, we have our 0, then 1 over n. That would be the right-hand endpoint of the first interval. Then 2 over n, 3 over n, all the way up to n minus 1 over n. Note the 1 is n over n, and 0 is 0 over n. And those are going to represent how we take this interval from 0 to 1 and we break it up. And on each of these little subintervals, we need to draw an associated rectangle. And we're going to use the right-hand endpoint to determine the height. And despite what my picture might look like, pretend each of these have a base length which is exactly the same. And this is going to leave us with n rectangles whose areas we need to add up. And now I'm going to kind of zoom back out a little bit just to give us some space. So So we would like to determine R sub n. And what I need to do for R sub n is add up the areas of each of these individual rectangles. So starting with the first one, its base length is 1 over n, and we determine its height by substituting that right-hand endpoint, 1 over n, into the function f of x. Then we go to the second rectangle. It has base length 1 over n, and then we substitute the right-hand endpoint of that second subinterval into our function. So 2 over n squared. And then we take the area of the third rectangle, and we keep going. And we do this all the way until we get to that nth rectangle. So that would be 1 over n times n over n quantity squared. And this sum is going to represent R sub n, the right-hand estimate using n approximating rectangles. And our goal is to come up with a convenient formula representing this quantity, one that we can take the limit of. This is where our previous discussion involving sigma notation is going to come into play. So let's go ahead and just make a couple observations. The first observation I would like to make is we're adding up multiple terms, but they all have something in common. Note, each and every one of these quantities has this 1 over n representing the base length of the rectangle. So if we pull that 1 over n out, what's left over would be a 1 over n squared plus 2 squared over n squared, coming from that next term. And now hopefully the pattern is emerging. We see 3 squared over n squared, and we go all the way up to n squared over n squared. And I realize n squared over n squared is 1, but I'm trying to keep this general pattern. Note, each of these n terms that we're adding up also has something else in common. They all involve a 1 over n squared. So if we pull that 1 over n squared out and combine it with our 1 over n, it becomes a 1 over n cubed. And that 1 over n squared coming out of each term leaves us with a 1 plus 2 squared plus 3 squared, and so on. And hopefully that part is now looking familiar. The 1 sitting in there could just as easily be 1 squared. And we're adding up multiple terms with a common pattern. We can express this in sigma notation. So the 1 over n cubed hangs around out front, but everything in the square brackets is going to be a sum. We're summing up quantities of the form I squared, where I starts at 1 and it goes to n. And note, this is looking even better than expected because that sum is one of our common formulas from our first video dealing with this topic. When you sum from I equals 1 to n of I squared, and then we just recall this formula to the side, what you will get is n times n plus 1, and then remember it's a 2n plus 1 as the third term, and that's all divided by 6. So we have 1 over n cubed times n plus 1, 2n plus 1, all over 6. And this is going to give us our formula for R sub n. So what we have learned is that R sub n, the right-hand approximation to the area enclosed underneath this curve x squared from 0 to 1 using n approximating rectangles, is the quantity n times n plus 1 times 2n plus 1 all over 6 n cubed. And we're to the last step. So note, we have found a formula for R sub n. What we need to do now in order to calculate the area is calculate its limit. And before doing so, let me just pause briefly to mention that these common formulas from the end of the first video, this is where they're going to start coming into play, which is why they are useful for us to be able to recall. So the enclosed area that we are looking for is the limit as n approaches infinity of r sub n. And we know precisely how to express r sub n. It's this formula off to the right. And what I would like you to do is, thinking back to our discussion of limits at infinity, what do you think is the value of this limit? So maybe pause the video, give yourself 30, 45 seconds, and just really think back to our previous intuition. And hopefully you've paused the video, you've thought about this. Note what type of function this is. This is a rational function in n. And when you are taking a rational function and a limit as you approach infinity, you can compare the degrees. If you were to expand everything out in the top, it would be a degree 3 polynomial, and its leading coefficient would come from this 2. In the bottom, it's a degree 3 polynomial with leading coefficient 6. So from our previous work with taking limits as you approach infinity, we can divide those leading coefficients because it's the same degree in the top and the bottom. So this ends up being 2 over 6, which is 1/3. And this is the quantity that we were shooting for. So kind of our conclusion here to wrap this up, the area underneath the graph of the curve given by y equals x squared from x equals 0 to x equals 1 is 1/3. And note, we've explored this idea with one concrete example, x squared from 0 to 1. What we would now like to do is take this idea and see if we can explain how it should work, give ourselves a very nice procedural formulaic approach for a general function on a general interval. And that's what we'll do in our next video. So stay tuned and take care.